Green roofs offer significant benefits, both aesthetically and in extending the lifespan of a roof. Beyond their visual appeal, these systems are particularly valuable for stormwater control. Unlike conventional roofing types, green roofs significantly reduce runoff, and their effectiveness in managing stormwater is quantified by their annual capture effectiveness. We're seeing growing adoption of green roof systems, with some retail business groups, such as gas stations and large big-box stores, integrating them as a standard option in their designs to meet discharge permit requirements. You'll often see the term written as two words, green roof, but it's becoming increasingly common, reflecting its widespread use, to see it as a single word, green roof. In this section, we'll cover several key learning objectives. First, we will establish a clear definition of what a green roof is. Next, we will explore the methodology used to determine the annual capture of rain or the release of runoff, explaining how these figures are derived through simulations. Following that, we will demonstrate how to effectively use the BMPFast software. This will include guidance on data entry for annual mass removal analysis and understanding its output when applied to a green roof system. We will also specifically show how to use BMPFast when there are two catchments operating in parallel. Finally, we will apply these concepts through an illustrative example project. The green roof is essentially a vegetated roof system designed to utilize rainwater. The plants on the roof capture precipitation, using some of the water and transpiring the rest back into the air, which significantly reduces the amount of runoff from the roof. Beyond managing stormwater, green roofs offer several other benefits. They provide an extra layer of insulation, which can lead to reduced heating and cooling costs for the building, and they are also known to extend the lifespan of the roof by as much as 10 to 20 years. We generally categorize green roofs into two main types: active, also known as intensive, and passive or extensive systems. Active green roofs feature a deep growing medium, typically 5 inches or more, and are planted with a wide variety of plants. They can also incorporate hard surfaces and are often designed for public access, functioning as usable outdoor spaces. In contrast, passive green roofs have a shallower growing medium, usually around 3 to 4 inches deep. These systems are primarily designed for aesthetic purposes, with access limited to essential maintenance activities. The amount of water these roofs capture annually is highly dependent on the local rainfall volume and the duration of dry periods between rain events. Here, we're looking at typical cross-sections of a green roof, which commonly feature a lightweight growing media. A significant benefit of these systems is their ability to address high wind conditions. For instance, one of the earliest passive green roofs in Florida, located in Bonita Bay, famously remained intact after a nearby hurricane, when many other roofs in the area were destroyed. This demonstrates how green roofs can provide additional protection against heavy winds. Beyond wind resistance, several factors influence how a green roof manages rainfall. The depth of the growing media, the specific plants selected, and the overall storage capacity within the system all affect the rainfall excess or the volume of runoff. Early monitoring of these roofs consistently noted a significant reduction in the volume of runoff compared to the total volume of rainfall, highlighting their effectiveness in stormwater management. When considering green roofs, it's crucial to understand the structural support needed for the plants and growing media. The numbers you see here represent example unit weights, measured in pounds per cubic foot. While most green roofs are designed to support a weight of up to 25 pounds per cubic foot, designs supporting up to 70 pounds per cubic foot have also been reported, with other variations falling in between, such as up to 35 or 50 pounds per cubic foot. The photograph on the bottom left of your screen shows a green roof located on the campus of the University of Central Florida. This particular roof was instrumental in documenting its performance over 10 years of operation. Researchers monitored the temperature of this green roof, revealing significantly less fluctuation compared to an adjacent roof covered only with a membrane. This finding is important because it suggests the green roof membrane would likely last longer due to reduced thermal stress. Additionally, the runoff volume was also monitored, and the study documented a noticeable reduction in runoff relative to the amount of rainfall received. For more additional pictures and detailed information on various product lines, you can visit greenroofs.com. Here we have another example of a green roof installation in Florida, specifically at a car sales headquarters in Claremont. This particular green roof was ingeniously designed and operated to serve a dual purpose, providing water for both car washing and site irrigation. Beyond water reclamation, it was also integrated directly with the building's air handling system, a feature that significantly increased the operating efficiency of the air conditioning. Over a 1-year period, documentation showed that the collected runoff volume from this green roof was notably less than the total rainfall volume, demonstrating its effectiveness in managing stormwater. The Florida Showcase Green Enviro Home provides an excellent case study for residential site design, incorporating features like green roofs and large storage tanks. At this facility, over 4,500 gallons of rainwater could be collected and stored. This demonstrates how a well-designed green roof system can significantly save money and reduce harmful runoff pollution. Over a 2-year period, extensive measurements were taken to analyze water quality and discharge from these systems. The stored water was then put to practical use for non-potable needs within the home and for irrigating the surrounding landscape. Beyond this particular project, green roof runoff water has found diverse applications in other Florida locations, including for vehicle cleaning, outdoor fountains, and even indoor display areas. This residential landscaping project is situated on Casey Key in Sarasota, a beautiful coastal region of Florida. For this particular home, the design thoughtfully incorporated a variety of native plants perfectly suited for the local environment. We see examples like mondo grass, muhly grass, and kunti, alongside other carefully selected specimen plants, all nestled within a bed of rounded rock. These plants thrive in a specialized bold and gold, or B&G, growing media. A key sustainable feature of this design was its approach to water management. All stormwater runoff was collected and efficiently reused on site. Remarkably, the annual volume of runoff generated was less than the total rainfall received throughout the year. This project was a collaboration brought to life by John Wheeler Landscaping and BAM. The University of Central Florida's Student Union Green Roof was installed in March of 2005 and achieved full coverage with vegetation in approximately 1 year. This project served a dual purpose: to protect the underlying roof membrane and to meticulously document runoff removal and capture in relation to rainfall. All native vegetation was used for the roof's design. Over a period of 10 years, significant data on rainfall and runoff volumes were collected, providing valuable insights into green roof performance. The energy benefits were also thoroughly analyzed by the Florida Solar Energy Center, or FSEC, revealing a heat reduction of about 45% in a year. An interesting ancillary effect was observed with office spaces that had a direct view of the green roof. Their rent increased by $8 per square foot annually. From a technical perspective, it's important to understand some key findings. Although there was no intentional storage designed into this specific green roof, a back-calculated non-directly connected impervious area curve number, or CN value, of 95 is now recommended for green roofs. This value was derived by considering the absence of a directly connected impervious area and comparing it to the simulated capture volumes reported in Appendix N of the applicant's handbook. Due to the typical lack of intentional storage or specific treatment depth in green roof designs, the retention tables found in Appendix O of the handbook cannot generally be applied for their analysis. This slide highlights the Escambia County Office Complex, which houses one of the largest experimental green roofs in Florida, spanning approximately 33,000 square feet. This significant project, built in 2010, was made possible through the collaborative efforts of Escambia County, Bay Design Architects, A.E. New Jr., and the Florida Department of Environmental Protection, with additional vision and technologies provided by the University of Central Florida. This innovative green roof serves important experimental purposes and effectively manages stormwater runoff, absorbing around 20,000 gallons of water annually. When selecting plants for a green roof, especially in a region like Florida. The most commonly used species are native plants. These are incredibly well suited for both active and passive green roof systems due to their natural adaptability to the local climate. Some excellent examples that you'll frequently see include muhly grass, known for its resilience and beautiful feathery plumes, as well as mimosa, black-eyed Susan, and blanket flower. These selections are not only robust enough to thrive in the unique conditions of a rooftop environment, but also contribute to local biodiversity and ecological health. When selecting plants for green roofs, you actually have many different native options available to you. For instance, species like upright rosemary, sandcord grass, dune sunflower, and red basil are all excellent choices that thrive in these environments. A significant advantage of these green roof designs, particularly passive ones, is their relatively limited maintenance requirements. In fact, the maintenance frequency is usually comparable to what you'd expect for ground-level plants, often only needing attention about 2 to 4 times a year. However, it's important to remember that if you're seeking annual removal credit, a detailed maintenance plan must be submitted as part of your project. Our study on green roof efficiency in Florida utilized data from 18 distinct sites across the state. These locations were specifically chosen because they provided hourly rainfall data from rain gauges, which was crucial for accurately simulating rainfall and runoff. We determined removal curves as a function of various cistern sizes, calculating the corresponding storage and curve number, or CN, values, to achieve a runoff volume coefficient, or ROC, between 0.4 and 0.5. A curve number of 95 was recommended. This recommendation was then validated against the ROC tables provided in the applicant's handbook. Operationally, irrigation was applied twice per week, with each application delivering approximately 1/4 inch of water. It's important to note that there was no intentional storage designed on the roof itself. Here we're looking at an example of the capture effectiveness of a green roof when integrated with a cistern. Drawing from research conducted by Dr. Harden and published in an FDEP report, this particular example comes from the West Palm Beach area, one of 18 sites studied across the state. Without the added storage of a cistern, a green roof on its own will capture a fraction of the stormwater runoff. In this specific case, the green roof alone captured about 42% of the water. However, as the storage volume within the cistern increases, the overall capture percentage also significantly increases. While we use the term cistern here, you'll also encounter other terms for similar storage solutions, such as underground vaults or tanks. As a standalone best management practice, a green roof system with a cistern can meet a substantial portion of specified capture standards, particularly in redevelopment projects. For many projects, this combination has been granted significant credit, often over 70%, for both total phosphorus and total nitrogen removal. When comparing green roof designs in South Florida, a standard practice for cistern storage involves allocating 1 to 2 gallons of storage capacity for every square foot of the roof area. Our examination, based on 8 different removal curves, demonstrates the considerable variability in water capture efficiency, both with and without a cistern. These simulations also crucially account for the use of the collected cistern water to irrigate the green roof plants, typically at a frequency of 2 times per week. When we consider the curve number, or CN value, for a green roof, it's calculated by understanding the annual runoff fraction of rainfall. A key aspect here is recognizing that there isn't a defined directly connected impervious area, or DCIA, and there's no intentional storage designed into the system, meaning the treatment depth is considered 0. Our observations from a 4-inch green roof show that the rainfall excess, which is the runoff, typically ranges from about 0.4 to 0.5 of the total rainfall. This finding was further verified using the green roof at the University of Central Florida. Building on these insights, simulations performed by Harper, specifically the ROC simulations, demonstrated that when we assume a DCIA of 0, the resulting curve number value for these systems comes out to approximately 95 across all 5 of our state's meteorological zones. Therefore, based on this consistent data and analysis, we recommend using a curve number value of 95 for green roofs. This value can be easily validated, either by using a discovery tool like BMPFast or by performing hand calculations using the tables provided in Volume 1 of the applicant's handbook. When green roofs are utilized as a catchment area, it's important to consider that wind and rain can deposit materials from adjacent areas onto the roof surface. In practice, the pollutant loading from a green roof is typically assigned the same values as the adjacent land use. To give you some context, a conventional roof, for example, might have a total nitrogen loading of 1.050 milligrams per liter and total phosphorus at 0.12 milligrams per liter. Residential single-family areas tend to have higher loadings, around 1.645 milligrams per liter for total nitrogen and 0.20 for total phosphorus, while light industrial areas fall somewhere in between. Regarding treatment, limited concentration reduction has been observed when cisterns are used with green roofs. This is primarily because the runoff from a green roof contains very low particulate fractions for both total nitrogen and total phosphorus. This green roof runoff is often termed filtrate, which itself indicates these low particulate levels, meaning there's often no credit given for concentration reduction. Despite this, green roofs are indeed considered a valuable best management practice, or BMP, and are explicitly listed under the Green Stormwater Infrastructure Alternatives in the applicant's handbook, Volume 1, Appendix O. Let's walk through the project description for a redevelopment in the Tampa area. This project involves transforming a 2-acre low-intensity commercial site into a light industrial area. Key parameters like the building roof area, which is 30,180 square feet, and the ground level area of 1.31 acres, along with the runoff characteristics, will remain consistent. Currently, there are no existing best management practices in place. For the new light industrial building, a green roof is planned to cover the entire structure. To manage the runoff from this green roof, a cistern will be used. Based on a target of a commercially available 30,000-gallon tank, we've calculated that the storage depth for the cistern needs to be 1.6 inches. This depth is derived directly from the cistern storage volume formula shown on the slide, factoring in the green roof area. Beyond the roof, a portion of the ground green space will be utilized for a retention best management practice. This retention basin is designed with a storage volume of 0.167 acre-feet before overflow. For this ground-level basin, the treatment depth calculates to 1.53 inches. It's crucial to understand that both the building's cistern and this ground-level retention basin discharge separately and directly to the sewer system. They operate in parallel, rather than in series. The overall aim here is to use software like BMPFast to accurately calculate the annual capture effectiveness of these combined green infrastructure elements. Let's begin by looking at the input for our site and watershed data. Here, we're considering two distinct catchments: the green roof and the ground level. We'll start by examining the data for the green roof catchment. When we look at the land use loading concentration for a green roof, it's roughly comparable to that of light industrial land use. However, it's crucial to remember that the runoff volume from a green roof is uniquely affected by its specific media and its inherent storage capabilities. For example, reported field work by Hardin on a 4-inch deep green roof at this site indicated an average annual runoff volume of approximately 42% of the total rainfall. This translates to a curve number, or CN, of about 95. When you're working with your own catchment data, it's important to use a curve number that accurately reflects the media on the roof and the specific rain zone you're in. For most typical applications, a green roof curve number of 95 is a widely accepted value. Our next step involves entering the specific data for the ground catchment. For this, it's crucial to input the various ground-level land uses, along with their corresponding curve number, or CN, and disconnected impervious area, DCIA, values. You'll notice that since the CN and DCIA values are specified as the same for both the pre-development and post-development conditions, the total runoff volume calculated will also remain consistent. However, despite this consistent runoff volume, there's a significant difference in the event mean concentrations, or EMCs, across these different land uses. This variation in EMCs means that even with the same runoff volume, the overall pollutant loadings will indeed be different between the pre- and post conditions. Here we see the results of our treatment worksheets for both the green roof and the ground level retention areas. For catchment 1, which utilizes a green roof, a cistern is employed to store and reuse the runoff. This system is designed with a storage capacity of 1.6 inches, which equates to roughly 1 gallon of cistern capacity per square foot of green roof. Given the project's location in the Tampa area, the rainfall data for our simulations was sourced from a local Tampa station. Based on the BMPFast printout, this green roof system is expected to achieve an annual runoff removal rate of 73.8%. Moving to catchment 2, which involves ground level retention, a proposed treatment volume of 0.167 acre-feet is designed to remove a significant 89.6% of both the runoff water and its associated mass. When setting up these systems, remember to go to the Configuration button to accurately enter the specific configurations and best management practices used for each catchment. You'll then configure each catchment to either lead directly to the main outlet area or be set up in a parallel arrangement. This slide summarizes a key outcome when a green roof and a retention area both discharge in parallel into the same sewer system, eventually reaching a surface water body. The loadings from these areas are added together. Here, we're looking at a redevelopment case where effective best management practices, specifically a green roof and a retention area, were implemented. These BMPs successfully met the specified loading targets, such as 45% total nitrogen and 80% total phosphorus, achieving an impressive 84.71% annual removal. Crucially, the numbers displayed highlight the significant impact on runoff volume. Before redevelopment, without any BMPs, the site generated 4.36 acre-feet per year of runoff. After redevelopment, with the green roof and retention area in place, the post-condition runoff volume was dramatically reduced to just 0.63 acre-feet per year. This substantial decrease in runoff volume is a critical calculation, often mandated and highly valued in various stormwater management programs, and tools like BMPFast can handle all these complex calculations and reporting efficiently. Let's take a moment to review what we've covered in this module. We started by defining what a green roof is, discussing its essential components, and distinguishing between the two generally recognized types. We then delved into some practical applications by looking at simulations conducted for 18 different locations across Florida. These simulations helped us calculate the annual capture of rainfall and the subsequent discharge from a green roof. We saw how this effectiveness, representing the retention of rain as a fraction of total rainfall, is influenced by factors like the use of a cistern and irrigation. Specifically, we noted that cisterns are frequently incorporated to store runoff water, which can then be used for irrigation on the green roof, typically at a rate of twice per week. This reuse of water significantly reduces the annual discharge. Finally, we walked through an example project to demonstrate how to use the BMPFast software for data entry and to perform an annual mass removal analysis. A crucial takeaway from this demonstration is the importance of consistently saving your project file, which has a BMPT extension. This ensures your data is secure for future reference, permit filing, or any further analysis you might need to conduct. This concludes our exploration of the capture effectiveness of a green roof. Throughout this module, you also gained practical experience in using the BMPFast model, applying this knowledge to scenarios involving multiple catchments where discharges flow in parallel to a receiving surface water. We encourage you to review other learning modules as needed to reinforce your understanding and to consider taking the competency test. For more details on the self-test, please refer to the module specifically dedicated to that topic. Thank you for your participation.